早上好，老师。
你好。
你好吗？
很好，谢谢你呢。
我也很好，老师。
You have improved. I think you have made a great progression. And
Thank you, 老师。
we cannot.
老师。
Yeah.
Sorry, 老师，you say?
I say when you speak Chinese, there's not too much accent.
I just haven't spoken Chinese in a while. I need to start speaking again, 老师。
What did you want to say before?
I want to ask you, which chapter are we ending on?
9. We have 9 chapters in total this semester.
When are we writing our exams? In 2 weeks.
Yeah, 3 weeks. Now we are.
Okay.
Yeah, we have still 3 complete weeks. That means we have 9. Yeah, 9 times of classes, except this one.
Okay, no, that's okay. That's good news.
Yeah, so we have plenty of time to finish our last 2 chapters. Yeah.
So then we'll have revision, 老师。
Yeah, we can have revision.
Okay.
And according to what I have received as information, perhaps the exam will be late. That means perhaps the university will wait for your return. And yeah, for the exam, normally it's also a writing exam.
Okay.
Yeah, I think because they ask us to give them some to give them some materials. That's why I think normally the exam will be happened after your return to China, and it will be as usual. That means it will be a writing exam. It's everything.
Okay, that's good news.
Yeah. So it's important that after, if we revise, it's better that you keep some. Yeah, or I will try to arrange some revision materials for you, and you can keep it. Yeah, it's better to keep it well, because I'm not sure when will be the
that'll be
exam.
fantastic, 老师.
Yeah. And before, normally here in China, other students, I think graduated students will be back for the first. Later we'll one group by one group will return back to our campus. But for the moment, we have no detailed information. Yeah. And Roy said it's not now. It is afternoon. Yeah. In China, it's afternoon. It's for sure that we are not.
It's afternoon in China. It's so boring in South Africa.
With the latency, we have different time notion now. And for the question of Fasor, it's not for sure. It's not sure, but for the moment, the phenomena, we haven't got very clear information for the moment.
Okay, so it depends, right, ma'am?
Pardon?
So it depends on a lot of things. About the notice also that we are going to have online examination or not.
Yeah, perhaps. But now they ask us to prepare some materials for writing exams. That's why I say perhaps with a big possibility it may be a writing exam after after the return of everyone. I think I'm not sure because we cannot even decide when will be the return date.
Okay.
Yeah. Um, it's very complicated this semester. Yeah. Also, after in about 1 month like this, I will ask for the I will ask for a period of break. That's that means if you have exams during that period, I will not be there. Um, so I will try to keep in contact with you, but perhaps it will be a little too difficult. I will try. What's important is that during this period and especially I think the last week of our semester. That means at the end of this month, April, we'll revise this software engineering. And if I have prepared some materials for you, keep them well. And if the exam happens later, you should revise it by yourself also. I will revise it with you at the end of this semester. But as the exam, it will not be just after the classes. So it's better. Thank you, Faso. It's better that you can keep the revision materials by yourself and revise well before the exam. Okay. So we will continue. Yeah. Perhaps as usual, we will begin by some revision, some small summary of what we have introduced, discussed yesterday. The principle of our courses of yesterday, we had an introduction of the software testing. We have talked about some notions about some notions regarding to software testing. We have said that there are three conditions. We have said that the ultimate objective of verification and validation processes is to establish confidence that the software system is fit for purpose. This means that the system must be good enough for its intended use. And we have introduced three conditions which decide the level of required confidence. Do you remember these three conditions? Marketing environment. Perfect. Thank you, Saji. Yeah, we have these three conditions to decide the level of required confidence. for the verification, the validation processes during the software testing. For the software purpose, we say that the more critical the software, the more important that it is reliable. Yeah, for example, the level of confidence required for software used to control a safety critical system is much higher than that required for a prototype that has been developed to demonstrate new product ideas. Okay, yeah, this part we have in the slide. It was here, yeah. Here depends on systems purpose, user expectations, and the marketing environment. We can decide the level of confidence. And for the user expectations, yeah, because of the experiences with the bugging, unreliable software of users, they have low expectations of software quality. They are not surprised when their software fails. So when a new system is installed, users may tolerate failures because the benefits of use outweigh the cost of failure recovery. And in these situations, we may not need to devote as much time to testing the software. However, as software matures, users expect it to become more reliable. So, more thorough testing of later versions may be required. So you see, with the user expectations, we can also have different levels of different levels of confidence, required confidence. And the third one is the marketing environment. I said here, when a system is marketed, the sellers of the system must take into account competing products and the price that customers are willing to pay for a system and the required schedule for delivering that system. In a competitive environment, a software company may decide to release a program before it has been fully tested and debugged because they want to be the first into the market. So, if a software product is very cheap, users may be willing to tolerate a lower level of reliability. You see, the reliability and the confidence level depends also on the marketing environment. These are three conditions to decide the level of required confidence or reliability. And then we have talked about three advantages of software inspection over testing. The first advantage is that during testing, errors can hide or mask other errors. Second one is incomplete versions of our system can be inspected without additional costs. And the third one is that just as searching for program defects, an inspection can also consider broader quality attributes of a program. These are advantages of program inspections. Later, we have talked about another very important thing is the 3 stages of testing. Especially for a commercial software system. Development testing, release testing, very good. Thank you, Saji, I'm sorry. And another one. User testing, exactly, perfect. These are 3 stages to go through during our software testing. We had the introduction here. Is here. For the 3 stages of testing, we have talked about the development testing, where the system is tested during development to discover bugs and defects. The release testing, where a separate testing team tests a complete version of the system before it is released to users. And the objective of this release testing is to check that the system meets the requirements of system stakeholders. And for the development testing, mostly it's the system designers and the programmers who are involved in this testing process. And for the user testing, where users or potential users of a system test the system in their own environment. For software products, the user may be an internal marketing group who decide if the system can be marketed, released, and sold. So acceptance testing is one type of user testing where the customer formally tests a system to decide if it should be accepted from the system supplier or if further development is required. These are 3 stages. Three stages of testing. Now we'll talk about these 3 stages in detail from now. So we'll begin by the first stage, which is the development testing. For the development testing, it includes all testing activities that's carried out by the team developing the system. Here, for this stage, as we said before, the tester of the software is usually the programmer, the developer, the system designers. So it's the workers who developed that software test the software. Sometimes it's not always like this. Some development process use programmer-tester pairs, where each programmer has an associated tester who develops, tests, and assists with the testing process. As when we develop a system, later perhaps it's difficult for oneself to test it, as we may have the dependency, perhaps we can say past dependency, which avoids us from detecting the errors. For some critical systems, we may use a more formal process with a separate testing group within the development team. And they are responsible for developing tests and maintaining detailed records of tested results. Here, these 3 levels of granularity shows different kinds of testing during the development. You see, the testing may be carried out at the unit testing level. Here, individual program units or object classes are tested. And we should focus on testing the functionality of objects or methods. You see, it's for each unit, that means each individual program or each object classes. And second level is the component testing. Here, several individual units are integrated to create composite components. Component testing should focus on testing component interfaces. So the difference between this unit testing and the component testing here is just one individual program unit. And with the component testing, we have the integration of several individual units. And for the system testing, some or all of the components in our system are integrated and the system is tested as a whole. System testing should focus on testing component interactions. You see the level deepers gradually. Here, for the system testing, it is a collection or an integration of some components. So here individual units, several units compose the component, and then several or some components compose the system. So you see we have 3 levels of granularity. Here are the relationships between them. This part is important too, to know during the development, testing can be carried out at these 3 levels of granularity. In fact, development testing is primarily a defect testing process. According to what we have said before, the 2 objectives of testing. We have one is the validation testing and the second one is the defect testing. With the development testing, the objective of testing is to discover bugs in the software. So usually here, the development testing is interleaved with debugging. The process of locating problems with the code and changing the program to fix these problems. Debug, I think you have already heard of it or have already experienced with it. When we are talking about this, I have think of another question for you. As we have said just then, sorry for the late. Don't worry, Shibli. And now we'll talk about the 2 goals of the testing process. Do you remember? It's okay, Shibli. And now we'll revise the 2 goals of the testing process. We have said just then we have mentioned for the development testing. Do you remember the 2 objectives of the testing process? We have mentioned it just then, and we have also revised it at the end of last class. Yeah, validation test. And defect, yeah. So what we have said just then, the development testing is for which one? Development testing is for which one? It's for validation testing or defect testing? Validation testing. Do you remember the differences between these two objectives? We said that for the validation testing, it's to test, it's to see if the system, we expect the system to perform correctly using a given set of test cases that reflect the system's expected use. That means for the validation testing, we want to demonstrate to the developer and the customer that the software meets its requirements. And for the defect testing, what we want is to discover situations in which the behavior of the software is incorrect, undesirable, or does not conform to its specification. That means to find some bugs and debugging. So in fact, for the development testing is rather the defect testing. Is it clear? And thank you, Roy, and Kaya for the answers. But yeah, it's we should make difference between these two objectives. The one is for the requirements, is the validation testing, is to validate that the system meets the requirements of customers. And the second objective is the defect testing, which is to ensure that the system works well, the system satisfies the specifications. So with the defect testing, we have some process of finding the bugs and debugging. This stage, the development testing is exactly a defect testing process, and the aim of testing is to discover bugs in the software. Also, we have the debugging process to locate problems with the code and change the program to fix these errors or these problems in the program. Okay. So we'll see that unit, and as here we have introduced these three levels of granularity. Now we'll look at them in detail one by one. Pay attention that here we have these three three levels of granularity. They are like a pyramid. Unit testing is the individual program units. That means the smallest unit. Then we have several individual units. We compose the component testing. Later, with some components, we have the system testing. So you see, it's the pyramid of this. Now we'll see the unit, the first one, the unit testing in detail. Unit testing is the process of testing program components. Yeah, it is the process of testing individual components in isolation. For example, we may test the methods or object classes. As we have said, individual functions or methods, they are the simplest type of component. And as we said before, all levels of granularity during development. All testings happened at these levels of granularity during the development. They are defect testing processes. So it's the same thing for the unit testing. It is a defect testing process. And when we are testing object classes, we should design. Here we have talked about different kinds of units. It's like the definition of units. Units may be individual functions or methods within an object. Units may be object classes with several attributes and methods. Units may be composite components with defined interfaces used to access their functionality. So you see, we can have different types of units, but keep in mind, units, usually they are the simplest type of component. So when we are testing object classes, we should design our tests to provide coverage of all the features of that object. It means that we should complete test coverage of a class involves testing all operations associated with that object. We should set and check or interrogate all object attributes associated with that object. We should also exercise the object in all possible states. That means we should put the object into all possible states. And we should simulate all events that cause a state change. Here, we have some special cases. If in an object there are some different relationships like the inheritance or generalization, these things make it more difficult to design object class tests as the information to be tested is not localized. So with these different relationships between object classes, the testing becomes more complicated. We cannot simply test an operation in a class where it is defined, and we cannot assume that it will not work as expected in the subclasses that inherit the operation. When we test one class, if it has some children, we have to also to test for the children. That's the inheritance implies. And the operations that is inherited may make assumptions about other operations and attributes. These may not be valid in some subclasses that inherit the operation. Therefore, we have to test the inherited operation in all of the contexts where it is used. So you see, when we are facing with some special cases like inheritance or generalization, we need to pay attention for the localization of different methods or objects. Here, we have an example of the weather station object. This figure, we have seen it before, I think. In this example, we have one single attribute, which is the identifier, and it is a constant. So, it is a constant that we have. It is set when the weather station is installed. Therefore, we need only to set a test that checks if it has been properly set up. And we need to define test cases for all of the methods associated with the object. These different methods, such as report weather, report status, etc. And ideally, we should test these methods in isolation. But in some cases, some test sequences are necessary. For example, we may need to test the method that shuts down the weather station instrument. We need to have executed the restart method. We need to go back to the figure in the 7th chapter, I think, to see this one. I'm not sure if I have it. Okay, I will. Not here. In the 7th chapter, normally we have this. Oh no, not there. Somewhere here. Yeah, here. As we have said, if we need to test shutdown, we need to restart. It's like the here, the state diagram. Yeah, we'll see its detail later. So you see here, like we said, we need to define test cases for report weather, calibrate, test, startup, and shutdown. All these objects, all these methods associated with the object should be tested. We can use our state model to identify sequences of state transitions to be tested and the event sequences to cause these transitions. This one, the state model, is just what we have, what I have found in the 7th chapter. We'll see it later. Yeah, here. You see, from this state model, we can identify different sequences of state transitions that have to be tested and define event sequences to force these transitions. In principle, we need to test every possible state transition sequence. although in practice, this may be too expensive. We can take some examples of state sequences that should be tested in this weather station. Can you? Yeah. Okay. How can I introduce it to you? Perhaps it's better that I zoom it. And we'll see. Yeah, here we have 3 sequences. Perhaps you can find other sequences here. So what we'll do now, as we have, we can have a break of 10 minutes now, but during the break, please check these. As you have already these 2 slides, I think, 2 PDFs. You can try to understand these 3 examples or 3 sequences from this state model. Then try to find other sequences. I will note for your attendance. We have more absence today. Shutdown, configuring, running, and controlled. Yeah, very good. Thank you, Roy. Yeah, you see here we have listed 3, and controlled is not conserved. That's why I can confirm it directly. You see here we have 3 examples. The first one is shutdown, running, and shutdown. It's like this. It's the this circle. And for the second one is configuring, running, testing here, and then transmitting, then running. Is this one. And for the third one is running, collecting, running, summarizing, transmitting, running is this one, this part. And for the example that Roy has given is this one, shutdown, configuring, running, and controlled. Yeah, it's this one. Very good. Thank you. So you see with our state model, we can have multiple sequences to be tested. Now we'll see a mechanism of testing, which is the automated testing. Whenever possible, unit testing should be automated so that tests are run and checked without manual intervention. In automated unit testing, we make use of a test automation framework such as JUnit to write down and run our program tests. So you see, it's automatic. It's not manual one. And the unit testing framework provides generic test classes that we extend to create specific test cases. They can then run all of the tests that we have implemented and report, often through some graphical user interface on the success of otherwise of the tests. Generally, we have 3 parts for our automated test, the first part is a setup part where we initialize the system with the test case, namely the inputs and expected outputs. So you see, for our automated testing, we need at first decide or initialize the inputs and expected outputs. Then we should call the automated testing. It's our core part where we call the object or method to be tested. Then we have an assertion part where we compare the result of the call with the expected result. You see, the expected result is given in the setup part. If the assertion evaluates to true, the test has been successful. If it is false, then it has failed. So this one is like the result of the testing. This is for the automated testing in the unit testing. And for unit testing, we should also choose, we should also keep we should also keep it effective. The test, to keep it effective, it is important that we choose effective unit test cases. As in most of time, testing is expensive and time consuming. So we need to pay attention when we choose effective unit test cases. You see here, when we say effectiveness with our unit test cases, it means two things. The first thing is that the test cases should show that when used as expected, the component that we are testing, that's what it is supposed to do. And the second one is that if there are defects in the component, these should be revealed by test cases. So you see, test cases cannot be chosen. We cannot choose the test cases randomly. We should have some basis to choose a test case. We should show that the component does what we want it to do, and we should also reveal the defects in the component. These are two things to mean the effectiveness here. Therefore, we should write two kinds of test cases. The first of these should reflect normal operation of our program and should show that the component works as expected. It corresponds to the first thing of effectiveness. And the second type should be based on testing experience of where common problems arise. It should use abnormal inputs to check that these are properly processed and do not crash the component. This second type of unit case test case corresponds to the second thing of the effectiveness. That means with these cases, we can find or we can reveal the defects in the component. For example, if we are testing a component that creates and initializes a new patient record, then our test case should show that the record exists in our database and that its fields have been set as specified. So you see, Here is to show the functionality of the system, and for this one, we need to include some unexpected situations with the system. Here, we can introduce two possible strategies that may be effective in helping us to choose test cases. The first one is the partition testing, where we identify groups of inputs that have common characteristics and should be processed in the same way. Here we should choose texts from within each of these groups. So each group of inputs having common characteristics. The second strategy is the guideline-based testing, where we use testing guidelines to choose test cases. These guidelines reflect previous experiences of the kinds of errors that programmers often make when developing components. You see here, it corresponds also to the two things of effectiveness. The first one is to, it's about the expectations or the requirements of our system, and the second one is to reveal the defects in the system. So with this, the first strategy, partition testing, we have the input data and the output results. They often fall into different classes where all members of a class are related. As same here, you see here, we should identify groups of inputs that have common characteristics. So we should at first partition the input data into different classes where they have common characteristics. And each of these classes is an equivalence partition or domain where the program behaves in an equivalent way for each class member. Here, that means this part, equivalence behavior, because they have equivalent behavior in this equivalent partition. Each member of these classes, they have equivalent behavior. So we call these classes equivalent partition. And one systematic approach to test case design is based on identifying all input and output partitions for a system or component. And test cases are designed so that the inputs or outputs lie within these partitions. Partition testing can be used to design test cases for both systems and components. Also, some examples of these classes, how to partition them as equivalent partition. We can classify them by some characteristics like positive numbers, negative numbers, menu selections, etc. Once we can classify them like this, we can consider them as an equivalence partition. And programs normally behave in a comparable way for all members of a class. That means for all members in our input equivalence partition classes. That is, if we test a program that does a computation and requires two positive numbers, then we would expect that the program to behave in the same way for all positive numbers. That's why we call it equivalence partition. And test cases should be chosen from each partition. Here we have an example. A figure to show the principle of equivalence partition. In this figure, this large shaded ellipse on the left represents the set of all possible inputs. You see, here are all possible inputs to the program that is being tested. The smaller unshaded ellipse like this, they represent equivalence partition, input equivalence partitions. A program being tested should process all of the members of an input equivalence partition in the same way. And output equivalence partitions are partitions within which all of the outputs have something in common. Sometimes there is a one mapping between input and output equivalence partitions. However, this is not always the case, and we may need to define a separate input equivalence partition where the only common characteristics of the inputs is that they generate outputs within the same output partition. And the shaded area in the left, this part, left ellipse represents inputs that are invalid, that are not valid. And the shaded area, this part, in the right ellipse represents exceptions that may occur. For example, some responses to invalid inputs. So you see, with this method, we need to pour the input data and output results into different classes with common characteristics. And once we have identified a set of partitions, we may have different, once we have the partitions, we can choose test cases from each of these partitions. A good rule for test case selection is to choose test cases on the boundaries, like this, the here boundaries of the partitions, plus cases close to the midpoint, like here, of the partition. The reason for this is that designers and programmers tend to consider typical values of inputs when developing our system. And we test these by choosing the middle point of the partition. Boundary values are often atypical. So they are sometimes overlooked by developers. Program failures often occur when processing these atypical values. You see with these partitions by using the program specification or user documentation, and from experience, where we predict the classes of input value that are likely to detect errors. For this one, say our program specification states that the program accepts 4 to 10 inputs, which are 5-digit integers greater than 10,000. We use this information to identify the input partitions and possible test input values. As shown in this figure, you see we classify them by number of input values less than 4, more than 10, and we search for the boundaries 3, 4, 10, 11, and the middle point 7. And for this one, you see less than, for 4 digits, we have 9999, 9,999. And for this part, I'm sorry, we have the boundary for this part and the middle point for this part. So we see that equivalence partition is an effective approach to testing because it helps account for errors that programmers often make when processing inputs at the edge of partitions. We can also use testing guidelines to help choose test cases. And guidelines encapsulate knowledge of what kind of test cases are effective for discovering errors. For example, when we are testing programs with sequences, arrays, or lists, guidelines that could help reveal defects. Some defects like this. The first one is test software with sequences which have only one single value. Programmers naturally think of sequences as made of several values, and sometimes they embed this assumption in their programs. Consequently, if presented in a single value sequence, a program may not work properly. So you see here is one kind of defect. And the second one is to use different sequences of different sizes in different texts. With this way, we can decrease the chances that a program with defects will accidentally produce a correct output because of some accidental characteristics of the input. We may also derive tests so that the first, middle, and last elements of the sequence are accessed. This approach reveals problems at partition boundaries. As what we have seen before, we normally choose the cases with the boundaries and the middle point. We have many examples of guidelines that can be used in test case design. And here we'll list 5 general guidelines. The first one is to choose inputs that force the system to generate all error messages. The second one is to design inputs that cause input buffers to overflow, and to repeat the same input or series of inputs numerous times, to force invalid outputs to be generated, and to force computation results to be too large or too small. These are 5 general guidelines that we propose here. But keep in mind, when we have experience with testing, we can develop our own guidelines about how to choose effective test cases. Also, the principles or the guidelines to choose different test cases may be different according to different types of systems too. And for the unit testing, we'll introduce till here. Now we'll see the component testing, as we say, it's composed of several units, components. Software components are often composite components that made up of several interacting objects. For example, in the weather station system, the reconfiguration component includes objects that deal with each aspect of the reconfiguration, and we can access the functionality of these objects through the defined component interface. We have the testing composite components, which should therefore focus on showing that the component interface behaves according to its specification. We can assume that unit tests on the individual objects within the component have been completed. So you see, for the component testing, we should keep in mind for some interaction between objects, and we should pay attention to the interface, and especially for the interface, we should pay attention. And this figure, it illustrates the idea of component interface testing. Suppose that these components A, B, and C, they are integrated to create a larger component or subsystems, and the test cases are not applied to individual components and not just to A, B, C. They have to be applied to the interface of the composite component created by combining these components. So you see, when we test them, it's with these interfaces. And interface errors in the composite component may not be detected by testing the individual objects, because these errors result from interactions between the objects in the component. We have different types of interface between program components, and consequently different types of interface error that can occur. Now we'll see these different interface errors. The objectives of interface testing are to detect faults due to interface errors or invalid assumptions about interfaces. And we have these 4 types of interface errors. The first one is the parameter interfaces. Data passed from one method or procedures to another. Here, these are interfaces in which data or sometimes function references are passed from one component to another, and methods in an object have a parameter interface. So we may have the parameter interfaces error. The second type of interface error is the shared memory interfaces. Block of memory is shared between procedures or functions. These are interfaces in which a block of memory is shared between components, and data is placed in the memory by one subsystem and retrieved from there by other subsystems. This type of interface is often used in embedded systems, where sensors create data that is retrieved and processed by other system components. We have the procedural interfaces. These are subsystem encapsulates a set of procedures to be called by other to be called by other subsystems. And these procedural interfaces, they are interfaces in which one component encapsulates a set of procedures, like said here. And we can call these set of procedures by other components. Objects and reusable components have this form of interfaces. And the fourth step is message passing interfaces. Subsystems request services from other subsystems. These are interfaces in which one component requests a service from another component by passing a message to it. And a return message includes the result of executing the service. Some object-oriented systems have this form of interface, just as like the client-server systems, we may have this one. Message passing interfaces error. So you see, interface errors are one of the most common forms of error in complex systems, as we have the interaction of different components of different objects. Usually, we can classify these errors into three classes. The first one is the interface misuse. A calling component calls another component and makes an error in the use of its interface. For example, the parameters in the wrong order. Here, this type of error is common with the parameter interfaces, where parameters may be of the wrong type or be passed in the wrong order, or the wrong number of parameters may be passed. It's for the interface misuse. And we have a second class of error is the interface misunderstanding. A calling component embeds assumptions about the behavior of the called component which are incorrect. Here, a calling component misunderstands the specification of the interface of the called component and makes assumptions about its behavior. The called component does not behave as expected, which then causes unexpected behavior in the calling component. For example, a binary search method may be called with a parameter that is an unordered array. The search would then fail. So you see, it's the interface misunderstanding. Then we have the third class, which is the timing errors. The called and the calling component operate at different speeds and out-of-date information is accessed. These kind of errors, usually they occur in real-time systems where we use a shared memory or a message passing interface. The producer of data and the consumer of data, they may operate at different speeds, as said here, at different speeds, unless particular care is taken in the interface design. The consumer can access out-of-date information because the producer of the information has not updated the shared interface information. So we can have this kind of error in some real-time systems with the latency between the called component and the calling components. We have some general guidelines for interface testing. The first one is to design tests so that parameters to a called procedure are at the extreme ends of their range. Here we need to examine the code to be tested and explicitly list each core to an external component. We should design a set of tests in which the value of the parameters to the external components are at the extreme ends of their range. These extreme values are most likely to reveal interface inconsistencies, like what's shown by our example. And the second guideline is always test pointer parameters with non-pointers. Here, where pointers are passed across an interface, always test the interface with non-pointer parameters. Yeah, I think this one, I'm not sure when you design some systems, perhaps you have been faced with this kind of problems, non-pointers. The third guideline is that to design tests which cause the component to fail. Where a component is called through a procedural interface, design tests that deliberately cause the component to fail, and differing failure assumptions are one of the most common specification misunderstandings. Then we have the fourth guideline, which is to use stress testing in message passing systems. This means that we should design tests that generate many more messages than are likely to occur in practice. And this is an effective way to reveal timing problems. You see here, our guidelines are also corresponding to the different types or different classes of interface errors. We have still the fifth guideline, which is that in shared memory systems, we should vary the order in which components are activated. Where several components interact through shared memory, design tests that vary the order in which these components are activated. These tests may reveal implicit assumptions made by the programmer about the order in which the shared data is produced and consumed. In some simulations, we may have this kind of problem too. So usually we use some methods to disturb or to disorder the data. Shuffle, for example, something like this, shuffle algorithm. Yeah. Okay, this is for this part, for the component testing. For the component testing, we have talked about, especially for some interface errors. And we have the last one, system testing. I think we'll introduce the system testing in the next class. Till here, do you have some questions? Some questions till here? Okay. Thank you, Kaya. And I have prepared one assignment for you. I will send it in the WeChat group. Yeah, for this part, yeah, the assignment I have it here. I think I can show you now. Here. This exercise. You see, for this assignment is it is quite easy. This assignment to explain the three levels of granularity. We have already talked about it multiple times, and then to explain the three types of interface error that can occur during the component interface testing. Is also a simple question. So please send this assignment, finish it, and send it to Roy before Monday. Yeah, another thing, for the last assignment, I have collected only six. Yeah, just six of you have sent your homework. It's better to finish it and send it as soon as possible. Okay. Pardon? I didn't. Yeah, I didn't get what you said. Now I will send the exercises in the group. Okay. So I'll say bye to you. Have a good time. Have a good weekend. Yeah. See you Monday. Bye bye. Bye bye.